So the next speaker, ladies and gentlemen, will be Ravikishore Velamuri. I hope I get his name correctly. You should pardon me if I didn't get it correctly.
You're
So he'll be
fine.
speaking on fundamentals of metabolomics and LCMS technology. Ravikishore holds an MS in biochemistry from Andhra University. He's a senior research scientist and laboratory director at HRI Labs. He has a robust biological background. He champions an integral omics approach and plays a pivotal role in the strategic advancement of omics capabilities and HRI labs and beyond. His strength lies in developing and validating innovative analytical methods and diagnosing complex issues with analytical instruments. He has extensive expertise as a core scientist in DMPK, ADME, in vitro experimentation, and bioanalytical assays using mass spectrometry. He specializes in LCMS-based methodologies for precision nutrition, medicine, and DMPK, ADME applications with a total of about 15 years of industrial experience, both in India and in the United States. His expertise includes advanced procedures for nutrient content, analysis using UHPLC, QTOF MS, and LCMS -MS, in addition to custom research with commitment to promoting innovation and excellence. Ladies and gentlemen, let us welcome Ravikishore Velamuri.
Hello, everyone.
Yeah, hello.
Hello. Good afternoon to someone and good morning to some others. I sent a request to present my screen, so I just got it. So I'll be sharing my screen. Can you all see my screen okay?
Yes, it's clear.
Can you all hear me okay?
100%.
Yeah, you're loud and clear.
Yeah,
Okay,
we can. Yes.
Okay, thank you. Thank you so much. Thank you so much for the organizers for setting up this platform to actually present my topic on this. So I was given this topic. Actually, I selected this topic. This is called Fundamentals of Metabolomics and LCMS Technology. In this, I talk about the basics and fundamentals of both these technologies and their integration and the application at our lab. I am, as the introduction says, I'm a postgraduate in biochemistry from Andhra University. And I started my career in drug metabolism and pharmacokinetics department as conducting experiments and also analytical division, where I was principally involved in all ADME assays, profiling the physicochemical properties and metabolic properties of new chemical entities, and also subsequently analyzing them with using LCMS. In that time, I was introduced to this new technology or advanced analytical technology called QTOF technology, which simplified our analysis, which I'll be talking shortly. And that is a prime example where that is used in the metabolomics, which I'll be shortly presenting. So thank you so much for this opportunity. I'm presenting my topic here. So here we'll go overview of metabolomics and with LCMS technology and LCMS analysis as the background. I'll show you a couple of examples of our projects conducted at Health Research Institute, which is my current organization. We are a small organization based in Iowa, United States, and also some future directions. So this is the overview of the presentation. I'll start with the basics of metabolomics. So as the name indicates, it is a comprehensive study of small molecules within the biological or environmental sample. So that means it can be different samples any biological sample, it is okay for the metabolomics to be conducted. So it aims to quantify and identify all metabolites in a cell, tissue, or organism to understand the metabolic state. That's the basic definition, and it also corresponds to other family of omics. When you profile genes, it is called a genome, and it is called genomics. Likewise, I have presented what is called as metabolomics. It's an entire profiling of metabolites, and the entire profile is called a metabolome, and the study of it is called metabolomics. And there is a technical definition which I have presented here. It is so this technical definition is basically what I understood after working with metabolomics for the past 4 to 5 years up until now. It is the study using advanced analytical technology in combination with the statistical and cheminformatic tools, because these are really important to characterize the metabolome and give a holistic understanding and the biological interpretation of the study. So the definition what I mentioned is from my understanding. So it talks about the interconnection and influence of physiology. For instance, if we are talking about human metabolome, it can contain both endogenous metabolites and also breakdown products. It also contains animal products in the human metabolome when we consume animal products like milk or meat or anything. So those also get integrated into the human metabolome. And because of the presence of microbes, as the presenter recently, the previous presenter mentioned about, I think Dr. Annie mentioned about close to 200,000 microbial metabolites present in the system. Yeah, and then if it is a plant-related diet, it also contains plant secondary metabolite that is also presented by Dr. Annie. She mentioned about plant secondary metabolites too. And if it is a chemical contamination in the body, as I think Addy presented, that presence of phthalates, bisphenol A, and other things in the system, that is also included as active metabolomic products. And if we consume any of the storage materials, the foods from storage materials, they also leach and they also come into the system. And if we are using some dyes in the foods, the food dyes are also a part of the metabolome, active metabolome, and there are environment pollutants too. So the study of the physiology is all influenced by these all interconnected factors. When we talk about metabolome, it all contains all these kinds of things. So these are all really diverse, and the scale of the metabolome is really large. So the sample types which are involved in the metabolomics are these plasma, urine, saliva, and tears. And as Dr. or Addy just mentioned, breath and also other kinds of biological samples can be used for metabolomics. The tissues, single cells, and plant related. So the time when the diet is taken to the time when the diet is metabolized to the body, the metabolome changes. So it's a snapshot of, or the dynamic. The metabolomics is really dynamic. It all depends on the time and the state and the disease state. All these affects the metabolome. So the steps in measuring technologies, this includes that what are the steps which are involved in the processing of metabolomic samples is any sample, as I mentioned, it may be plant, it may be tissue, or it may be a biofluid, or any related things are conducted and transformed into liquid phase. That means it's called extraction. And when they're extracted, they are actually subjected to the analytical platforms. And there are 3 different platforms in the metabolomic arena. These are NMR spectroscopy, which the gas chromatography, and the liquid chromatography. These 3 are the platforms for profiling the metabolome. And it can be a combination of them or an individual thing. And once the data is run through them, the next part is the massive data processing. So this is what I learned from my experience. So the data processing plays a crucial part in interpreting and also understanding the biology. So these are the steps involved in the processing. So for our this is the snapshot what I want to present here. Different samples, different source of sample types are subjected to LCMS. In our case, they are given, they are profiled, subjected to statistical analysis, and then that forms a base for the metabolome. So for the convenience of this talk, I want to present LCMS data because it dominates the metabolomics testing arena because of its exceptional detection sensitivity. And also, as you can see from the chart, the sensitivity is far advanced using LCMS technologies. In addition, it can be used simultaneously for hundreds, in fact, hundreds to thousands, and that is very normal in metabolomics, where it's not analysis of just one or few molecules, but it is an analysis of hundreds of molecules. So to cater that scale, LCMS is used where they can be detected simultaneously. So for our talk in the next thing, I focus my presentation to LCMS because LCMS is the as I mentioned, because of these postulates. And in addition to these, there are several other postulates of LCMS because of its ease of operation and its convenience and its literature in the metabolomics arena. I want to present further slides about the LCMS technologies. So what is LCMS? This is the technology which is giving me my prime time all these years. I really spent a huge time working on these technologies. So I really love this technology, and because it is it is a combination of liquid chromatography and mass spectrometry, which the liquid chromatography is the initial part which profiles the molecules or separates the molecules using analytical columns, which I'll be showing you shortly. And then once they are separated, they are detected with the mass spectrometry. So it is a combination of a hyphenated technology. So this is in brief of the liquid chromatography, where we will be using the reverse phase technology, the reverse phase chromatographic technology, which is using hydrophobic solid phase and separating it through the organic solvents. When you see that the current LCMS is advanced from HPLC to UPLC, where it handles the sample, where the sample is introduced, and it is separated through an analytical column. The analytical column has different chemistries like C18 or Helic. And then after the separation, oh yeah, that somebody is helping me. Thank you so much. The samples are then reintroduced into the mass spectrometry, and then they are detected. So what is mass spectrometry? This is a powerful technology which uses mass to charge ratio for detections. It is coupled with an ionization process, which I'll be showing you shortly. in principle, we'll be using electrospray ionization, even though atmospheric pressure chemical ionization is also there. Most of our analytes are in metabolomics. We'll be using ESI, electrospray ionization, followed by mass analyzers. There are two types of analyzers or more, but for the sake of the presentation, I wanted to present the quadrupole analyzer. Can you guys see this? I don't know what is happening here.
Yeah, I do.
Okay.
Wait, you are not fixing
Okay, so in terms of mass analyzers, we have quadrupole mass analyzer, time of flight mass analyzer, and hybrid time of flight analyzer. So what is quadrupole mass analyzer or quadrupole mass spectrometry, where the sample is introduced in a liquid form? When you see this, the sample is introduced in a liquid form, it is evaporated based on the source temperatures, and the droplets enter the quadrupoles, which are the set of parallel rods operating with radiating frequencies, and then the samples are the ions which are in vacuum are subjected to fragmentation, where in the fragmentation each molecule will create its own fingerprint, and then it is reintroduced into the other quadrupole, and then they are detected. So in principle, if you see that if molecules are introduced, they are fragmented, their daughter ions are then profiled. That's the principle what we will be using. If it is it's like a fragmentation. When it is fragmented, it gives a signature daughter ions. These are called daughter ions from base. These are very much unique for each and every molecule, where they are broken at their weaker bonds in the collision cell in the quadrupole, and then the fragments are then used to profile that particular molecule. So this technology, the quadrupole technology, is primarily used for quantifications, where samples are introduced, fragments are captured, and they are profiled, and these are used for quantifications. Can you all see the screen? Okay. Hello.
Yes, we can see.
Oh, okay, good.
I can hear you.
Yes,
Okay.
we can.
Good. So the triple quadrupole quantifications are used primarily to detect the unknowns and also quantify them according to their concentration levels. The second one is the quadrupole time of flight. This is a technology which evolved from mass spectrometry. It's an advanced thing where the molecules are separated based on their flight path times, and they are captured based on focusing kinetic energy of ions. So in principle, it contains a flight tube, and the time it takes to reach the detector is all captured. Again, the same principle is pretty much used, but it has its own postulates, the QTOF technology. So in this, we are using SWAT technology, where each and every molecule which goes is subjected to fragmentation, and the fragments are all captured. This is a sort of a game changer because of the scale and width of the potential where it can capture, fragment all the things, and capture all the fragments. So for instance, in the top MS, when we look at molecular weights close to 50 to 1,000 in that huge range, it scans the entire range, captures the fragments, and assigns the fragments to its own. And the software is used to sort of deconvolute the things and then reassign the fragments. In the LCMS technology, used in metabolomics, it is divided into two parts. One is an untargeted metabolomics, which aims to measure all metabolites. As I mentioned, it measures all metabolites at the same time. And in targeted metabolomics, where a predefined set of metabolites are measured and quantified. These are the two things which are used in metabolomics. To sum it up, one is hypothesis generating and another one is hypothesis testing. So untargeted, it's like looking at the snapshot of all molecules and at the same time, whereas targeted is focusing on certain molecules. So the goal in the metabolomics is to cover as much as metabolome as possible, because with one extraction procedure or with one analytical technology or with one kind of ionization, not all are all delivered at the same time. So the goal is, since the metabolomics is really complex, the goal is to cover as much as possible. So with this, what I gave you is the use of LCMS and untargeted and targeted sections in the presentation up until now. And then right now I'll be focusing on the applications of metabolomics, where I'll be particularly speaking about the central one, which is the agri and food. Even though the other applications are really important, for the sake of the presentation, I focused my attention towards the agri and food, where it is used for food component analysis, herbicide and pesticide detection, and soil and plant composition studies. Even though the nutritional and diet research is also closely associated with our area of work, right now for the convenience, I'll be presenting the next thing. So here, this is a little disclaimer that I'll be presenting certain slides which are really confidential. But it should sum up and it should give us some perspective on the metabolomic applications. So our lab is called HRA Labs. It is a non-profit organization located in Iowa, where we work. This is our mission statement. We make the invisible visible with our technologies. We'll be using mass spectrometry and molecular genetic approaches to make this happen. And we apply this technology to various fields, including human health. So the background of it is we'll be focusing on untargeted metabolomics. And our lab is a certified ISO laboratory. And we also are CLIA certified, so we can handle human samples for the studies. So this is our analogy. Just if you imagine a forest, everything in the forest is important, but once we focus on certain sections, then we can profile it in a better way. So we use mass spec. For instance, in the forest, we use mass specs to scan everything. That implies that the big trees are important, the under things are important, the shrubs are important, the herbs are important, and also the ground layer is important. So our focus is, what we are focusing is really important. So we will divide our work in such a way that we scan the entire forest to profile and give what are all there in the forest. So that's what we'll be using this technology for. For instance, if we have two kinds of samples, a treatment sample and a control sample, we profile both the things. When you can see in the slide, the one with green color is a control, and the one with the treatment is in red color. You can see when we focus on the sections from 2 minutes to 13 minutes in the LCMS profile, you can see clear differences where the control is completely different from the profile of the treatment group. So once we capture this in a whole thing, again, with the technology, we can be able to capture all the fragments of this time frame of both treatment and control, and that is that gives immense information about the profile. For instance, you can see from the chart, the retention time is equally important, the abundance is equally important, and also the M by M over Z is important. So the way we process the data is, first of all, we convert this table, the peaks, to tables and list using data softwares, and then we use this data to using open source tools like MSDial, and also that is accompanied with databases where the compound annotations and detections happen. So for instance, if we are focusing on certain M over Z, in this case, if we focus on the 20710 M over Z in the treatment versus control, you can see in the treatment, the levels of concentrations are really high, whereas in the control, it is low. When we profile this one molecular weight and then create a bar chart, comparison chart, you can see stark differences between these two. So this is how we do, and this is just for one M over Z. And with metabolomics technologies, we use hundreds, if not thousands of features to profile in this way. So manual curation of the data is really important in this case, and that's what we will be doing. So as I mentioned, we'll be using MSDial. It's an open source data software technology for processing the untargeted data, where we use the this to actually sum it up. So all the dots, what you see, are different molecular features, and the bar charts, what you see, are different samples. So the annotations, we follow certain rules where there are many detected compounds, out of which the named compounds are very limited, the unnamed compounds are so high, and that's the very much the data output what it is. So in the data processing, we convert this spectra to lists, and from lists to biology, and then we use certain examples. Okay, yeah, and up to until this part, what are all important things and what are all confounding things are addressed. And there are certain challenges with LCMS, and based on my previous experience, I could understand in a deeper way, and I'm able to sort them to some extent. And I want to present certain topics as an example here. This is called a wheat profiling. We applied this LCMS based metabolomics to an application of wheat, where we wanted to see the soil fertility and the conventional production system and organic production system. Again, wheat contains several semi-polar metabolites, including amino acids and some lipids and polyphenols. To profile all those things, we use this technology. After the spectra matching and biological interpretations, when we wanted to see it through the principal component analysis, where each and every group of sample, the dots what you see are different groups of wheat with different wheat samples, wheat varieties. They're all separately profiled, and in the PCA you can see their separation in a clear way. And the components of the metabolites used to separate them are shown here in the bar graph, where certain metabolites are increased in certain wheat varieties. The three colors what you see are three different wheat varieties, and the x-axis what you see are different metabolites, and the y-axis what you see are different intensities of the metabolites. From this chart you can clearly understand that certain molecules, certain metabolites are upregulated and certain are downregulated. And so the conclusion from that project what we got is close to only 10% or 12% of the unknown molecules what we can name them. The rest are unnamed, but the stark differences are of three different wheat varieties are clearly mentioned there, where few molecules are elevated, few are toned down, and likewise in organic and also conventional, that's how the profiling is. So it gave us some direction. So with that kind of thing, we applied this for different sample types, like potatoes, different potatoes, purple potatoes and normal potatoes. Squash, which is fresh versus old, where we could find huge differences between the amino acid levels. In fresh, they are very high versus stored, they are low. And we applied this for chicken samples raised on farm versus CAFO, and then there are differences. With like that, we have used it for sage, garden sage and rosemary, and blueberries and pistachios. With all these things, we really got interesting information, and we have published a certain of our works what from the same technology of metabolomics, and this is what as from the historic records of metabolomics was first applied to nutrient analysis way back in 20 years or ago. And we are supporting our farmers and our community here in Iowa by offering this service to them. We also are offering this service for food safety testing and nutrient testing samples. We are helping moms and consumers select their better food choices by using this technology. So why this is coming up always. So this is all our published work. And the future directions are what we understood after working with several projects is the advanced the analytical technology, the better the results. So adding more dimensions to the analytical technology and implementing some powerful AI tools and pattern recognition tools and machine learning tools would really enrich the data output and also the biological interpretations. So with this, my special acknowledgements to Dr. John Pagan, who is our chief scientist, who is always motivating and helping me to understand the deeper insights. I thank Ola, the program coordinator, for giving me this wonderful opportunity to present the metabolomics topic. And it is so encouraging for me and inspiring for me to even start one for my for my friends and family too. Thank you so much, and thank you all for your time.
Yeah,
Thank you very much. Thank you very much. A round of applause, digital applause for Dr. Kishore Velamuri. I hope I got the name. Pardon me if I did not.
Yeah, you're right.
Thank you very much. That was an elaborate lecture on the fundamentals of metabolomics and the technology of LCMS, how we have LCMS, GCMS, NMR as the options, but the advantage that LCMS has over the increased speed and sensitivity as well as the proteomics, metabolomics, genomics, and what's that last one I've forgotten now. Thank you very much. You broke down everything. The analytic platforms, we already talked about that. The LCM, the liquid chromatography itself, spoke about UPLC, as the advanced LCMS as ultra high performance mass spectrometry, reverse phase, liquid chromatography, and then many other things, the MS quadrupole, the fragmentation, and then the difference between untargeted and targeted metabolomics.
Journeys in the matrix. You're in the matrix.
Now I idea for targeted, there is a specific type of metabolites that are. You also spoke about the goal, which is to cover the metabolome and the challenges of the challenges of LCMS technology for analyzing metabolomics and a lot of other things, processing and analyzing data, as well as understanding the data itself. These are things that, these are hands-on techniques that one will need to get used to with more practice, or with extended practice in metabolomics research. Thank you very much, Dr. Kishore, once again. And thank you to all our presenters for the day. And Dr. Annie from Astrop, thank you very much for coming around to share your knowledge and experience in the field, in the area of metabolomics. And also thank you to MetabHole and DRTC for putting together this program. I can say for sure that personally, I am going away with quite a number of new information, and hopefully I'll be able to learn more. And this has triggered my interest in this area, and I believe that this applies to everybody, virtually everybody that has attended. At this point, I would like to invite the conveners of the program, as from MetabHole and DRTC, for the closing remarks and the next steps. Dr. Olakunle Jayesimi.
As we come to the end of this session, I want to extend my deepest gratitude to all the speakers, Pam Adeyeye, Dr. Ravi Kishore, and Dr. Annalise, the moderators, Olufemi, Olasheni, Sheyi. Really grateful, and to all the participants from across the world. So your engagements today is prove that metabolomics has a vital role to play in shaping the future, especially in Africa and underserved countries, all over the world, actually. And at MetabHole, we are actively collaborating and providing consultancy services to help institutions and companies solve their real-world challenges. And from research support to industry and clinical applications, we are committed to making metabolomics accessible, impactful, and transformative. What's next? You should mark your calendars. Our next webinar is set for April 19, 2025. So stay tuned for more details. And this is a call to action. We invite you to partner with us, whether you are in the universities or industry, biotech or pharma, a researcher, whatever institution. Let's work together to drive meaningful change. And if you miss anything or you want to catch up, the full recording of this event will be on YouTube for future references. And if you need resources or have any further questions, we're here to help. So reach out to us at info@metabole.com, or you can visit the website and read up more information from there. To connect with us directly, once again, thank you very much. We'll likely be sending you a survey, to get your feedback so that we can make improvement for subsequent webinars. Once again, thank you very much for attending this webinar.
Okay, good afternoon, good evening, good morning, everyone. Thank you very much, all the people that have participated in this webinar. We want to thank Dr. Olakunle and all the speakers. And I am sure the impact of the presentation of today will be huge in the research of all the participants. And like Dr. Olakunle has said, look forward to more engaging presentation from scientists from around the world in the field of metabolomics. Thank you very much, everyone. Thank you, the moderators as well. God bless you, everyone.